Hi! In our class in GED102, we saw how math manifests itself in the growth of plants and the reproduction of animals. What we've discussed so far is how math manifests in the visible world, what we can see, but we didn't really touch on stuff that is invisible to us, things we can't see, such as chaos, heat, and luck. How does math play into that? Hi, this is my presentation, Visualizing Mathematics as a Phenomenon, and I'm Lawrence Camacho, 3rd year PhEC. So we start with the concept of heat. How can we visualize heat when we can't see it? So the application I chose here was a previous project in my Math 149 class. It's temperature equilibrium distribution. It has applications of linear algebra and averages. So if you have the sun and it's projecting or it's heating up a conductor, what is the temperature inside the conductor as T approaches infinity or when it reaches equilibrium? Say we have this conductor with a shape like this. We have point P and around it is C, and it's bordered by 3 constant temperatures shown here. So if we label all of those temperatures and we assume that those temperatures are equal throughout time, we can observe that there are lines of equal temperature that's formed. Those lines are called isotherms. So knowing this, what can we do to find out the temperature at all points inside the conductor? We're going to use a property called mean value with regards to the context of thermal equilibrium. So it claims that at every point it can be represented by the average of its neighboring points. So point P's temperature is the average of the temperature of around C. So in this very less dense mesh, we can see that T sub O, T sub naught is equal to 0 plus 2 plus 0 plus 1 over 4. And here we have a denser mesh that we imposed on our conductor, and we can form 9 equations. Those 9 equations can be represented using linear algebra in the form of matrices. So we have T is equal to MT plus B. We can isolate T as the inverse of the identity matrix minus M times B. And doing all that, we can find the value of T at every point inside the conductor. So the software I used here, or the software we used here, was Matlab. And here is our code. The code will be in the description below. Running the program, we can have our previous solved matrix manually. Then we can have denser matrices. As we approach from a discrete looking point conductor, it sort of starts to look like a continuous temperature gradient shown here. So that's how you can visualize heat without really seeing heat through the use of mathematics. We move on to chaos. So in our physics class, in our theoretical mechanics class, we learned a dynamic system through our topic of coupled oscillations. That system is called a double pendulum. So the math here is very specific physics math and linear algebra. Here is an example of a double pendulum. It's swinging, and you kind of think that it's random, but actually the endpoints of those two rods are deterministic by its initial conditions. So long as you know the initial conditions, you can predict where those two masses will be, shown here in the diagram. So the description for the full derivation will be linked below since I don't have time. I will just be showing the 3 types of movement you can see. You have your chaotic movement, and then you have your 2 normal modes. A synchronous mode, which has 2 frequencies in opposite direction, and then synchronous mode, 1 frequency in 1 direction. It's like one pendulum. So what we think are random movements are just dynamic systems determined by its initial values. Random motions are just patterns that we don't understand yet. So now we move on to luck. So have you seen the show The Wall Philippines? Do you know the original name of the wall? It's like a pachinko board. It's called a Galton board after Sir Francis Galton. He proposed this idea. So imagine we have one sample and then we have the pachinko board, and then there's no pattern to it. As we increase the samples, you can sort of see now the pattern. The pattern is a normal distribution. So even if the initial conditions are unknown, dynamic systems will tend to act in certain predictable ways, depending depending on the likelihood of its event. Here I end on a quote. Whenever a large sample of chaotic elements are taken hand and marshaled in order of their magnitude, an unsuspected and most beautiful form of regularity proves to be latent all along. Sir Francis Galton. That's my presentation of visualizing mathematics as a phenomenon. I'm Lorenzo Camacho. Thank you for watching.